Hey guys, today we're going to be talking about how to solve problem 1, so let's get into it.
Hi, my name is Matthias Kubian and I am here to introduce the key concept of our presentation, conditional probability. Conditional probability measures the likelihood of event A conditional that event B has already happened. A simple way to phrase it is that the probability of A conditional upon B means that we are looking for the probability of A holding if we assume that B holds. It is not required for B to hold, but it does determine the conditional probability. We search for the variable and write it as P parenthesis A divided by B parenthesis, which is what that represents. That stands for conditional probability. If we take a look at the Venn diagram on the right side of the presentation, it shows that the conditional probability is the proportion of the intersection of A and B to the B space. Instead of comparing the proportion to the entirety of the sample, we just compare the intersection to the B space because that is what A is conditional upon. Finally, we reach the conditional probability formula. Remember, P parenthesis A divided by B parenthesis stands for conditional probability. The conditional probability is equal to probability of A and B over the probability of B. This will give us the probability of A assuming that B holds. To explain Bayes' rule. The formula for Bayes' rule can be written as P parenthesis H slash E parenthesis, which represents the probability of the hypothesis conditional upon the evidence. This can be solved by putting the probability of the evidence conditional upon the hypothesis times the probability of the hypothesis. All of that is divided by the probability of the evidence conditional upon the hypothesis times the probability of the hypothesis plus the probability of the evidence conditional not conditional upon the hypothesis times the probability of not the hypothesis. This basically is it's a mathematical way to revise probabilities when new evidence is observed. It allows us to update our beliefs about an uncertain event or hypothesis when we observe data. We usually know how likely certain evidence is if a hypothesis is true, but we want to know how likely this hypothesis is given the reverse direction. This is also known as the inverse probability problem. Bayes' rule enables rational belief revision based on new information, which makes it fundamental for reasoning under uncertainty.
Hello, my name is Ashley Parson, and I'm going to be talking about the slide of the different types of probabilities. As you noticed in our slide 3, we had the Bayes' rule diagram shown, and this slide is basically breaking down each of the rules of Bayes' rule. There's primary probability, which describes our initial belief about our event. The likelihood is the probability of seeing specific evidence, assuming particular hypotenuse is true, and that kind of explains the data on that. And then there's also posteriori probability is the update belief that the hypotenuse after consuming the new evidence. And lastly, there's margin probability, which refers to the overall probability of observed evidence across all positive hypotenuse and acting as a normalizing factor. Together, these come together to form the Bayes rule, allowing us to update in our new initial belief. As new information becomes available for us, and that kind of goes into our next slide.
Probabilities rule and assigning variables and calculating two conditional probabilities. Okay, so first we have to find the total probability of the crash. So as you can see on the image on the left, it shows the color values and the crash probability for each of the colors. In order to find the total crash probability, you have to multiply each color corresponding to its crash value and then add all of them up as shown in the image right here. In the end, the total crash probability is 0.15. So now we're going to use Bayes' rule to try and find the probability of blue and red. For Bayes' rule, you structure it by trying to find the hypothesis from the evidence. So, for example, right here for blue, it would be blue times crashed over blue divided by the crash value. You can see on the image on the right now that you just plug in all the values. So it would be 0.1 times 0.3 divided by 0.15, which equals 0.2. And same goes for the red. It's the same formula. You just change up the values. So for red, it would be 0.6 times 0.1 divided by 0.15, and that would equal 0.4. In conclusion, Bayes' formula is useful in being able to create better predictions by using the evidence to our favor. And the final calculations we have acquired is that the probability that Cynthia was assigned blue is 0.2, and the probability she was assigned red is 0.4. We hope you enjoyed our presentation and thank you for listening. Bye.